Next topic is the core ideas of a lean system. Core ideas of a lean system are reduced waste, reduced inventory, and reduced variability. So the first idea is reduced waste. We'll talk about 8 types of waste. Taiichi Ono is the former engineering of Toyota, and he says moving is not necessarily working. He identified 8 sources of waste as follows. First, overproduction. Manufacturing more of a product than required. So this will create inventory, but overproduction means more than inventory. It means manufacturing an item before it's needed or including more features than necessary. For example, a bike doesn't have to have a thermostat, but adding a thermostat to a bike is an example of overproduction. Next, transporting is a waste. It includes movement of materials, people, or information that adds no value. Next, defects. Defects are also waste because once we find a defect, we need to throw out all the inventory that has the same defect. Next, overprocessing is a waste. For example, stirring a fully mixed cup of coffee is overprocessing, or painting a car that's already painted in red is overprocessing. And overprocessing happens because the operator doesn't know what the exact standard of his work is. Next, unnecessary motion is a waste. This means excessive movement in the workplace, including both physical movement and that of data and files. And next, inventory is a waste. This is the biggest waste of all, and it includes raw materials, work in process inventory, or finished products. Next, waiting is a waste. Waiting is a direct consequence of inventory. Work in process is waiting to be processed. Machines are waiting for raw materials to arrive. Waiting is a type of waste. And finally, non-used employee talent is a waste. Your employee has a special talent. If you don't use it, you're wasting one of your resources. So far, we talked about 8 types of waste, and one of them was inventory. I want to emphasize the importance of reduced inventory. Reduced inventory can reveal hidden problems. Traditional systems use inventory to buffer the process from problems that cause disruption. So let's say you're producing cars in your assembly line, and there are many problems in your assembly line. Workers are trained poorly, and machines are breaking down frequently. Raw materials have quality problems. But if you build high inventory, these problems are hidden because, let's say, workers are trained poorly and they cannot work sometimes, then we can use inventory. The problem is hidden. The machines are break down frequently. When they're down, we can use inventory. The problem is hidden. When you have excess inventory, you can't see your problems clearly. However, if you lower your inventory, you start catching your problems. Let's say one of your machines breaks down, there's no inventory. Now you see the problem. You fix the machine. It's one of the advantages of holding low inventory. So now when you find a problem in your operation, how can you fix this? I want to turn to the idea of the PDCA cycle. This is a procedure that you use to find a solution to any problem you have. And it's also called Schurz cycle or Deming cycle. And this idea is called continuous improvement, Kaizen. And it means improving the process using a series of small progressive steps. And the key idea is using a series of steps. you're not going to try one step or two steps. We're going to try a series of steps until we find the solution. So how can we apply the PDCA cycle? First, we identify the problem, the area for improvement, and once you find the area for improvement, you can use the plan, do, check, and act cycle. This is the PDCA cycle. The first thing you need to do is plan. You study the process, identify the problem, set the goals, and develop the plan for improvement. In other words, you develop a potential solution for your problem. Next, do. You implement the solution on a test basis on a smaller scale, and you measure the improvement. And next, we study or check. We assess the plan. Is it working? Are the goals achieved? Next, act. If your solution is working, then we implement this on a larger scale. We're going to institutionalize improvement, and we're going to continue with a new problem. But if our solution doesn't work, we're going to do this cycle one more time. We're going to go to the plan part again. We're going to develop another solution, and we're going to implement this solution on a test basis, and then check and see if it's working or not. If it works, we implement this on a larger scale. If it's not working, we're going to do this cycle one more time. And we'll repeat this until we find the solution. So let me give you an example. Professor Smith teaches 5 sections of business statistics. In all of his sections, he noticed that a number of students attempted to cheat during tests. He decided to use the PDCA cycle. So this is the first cycle. You make a plan. He thinks a potential solution can be A, failing students who are cheating without prior warnings. And next, do. He implements solution A in one of his sections in a smaller scale. Next, check. He finds out solution A is not as effective as expected. So he finds out that students are still cheating during tests. So for act, he decides to try another solution. So he's going to do another cycle. So in the next cycle, so he plans, his next plan is implement solution B, which is giving verbal warnings to those who are cheating and failing them when cheating happens again. And next, do, he implements this solution in a smaller scale in one of his sections. And check, he finds out that solution B is effective. Students are not cheating anymore. So this is working. And next, he implements this solution in a larger scale in all of his sections. And we found a solution, and we can stop this cycle. To summarize, in continuous improvement, we're going to try a series of solutions until we find the solution. I want to turn to the idea of Six Sigma. So what does sigma represent? Sigma represents the standard deviation of a dataset. The standard deviation measures the variability of a dataset. So Six Sigma is related to the variability of a process. It says we need to reduce the variability of our product to reduce the defect rate. So let's look at the origin of Six Sigma. In the early 80s, Motorola had high defect rates. An engineer at Motorola found out that parts were coming from their suppliers, and the variations in the quality of these parts were responsible for the bad quality. So to have lower defects in the end products, the multiple parts that are going into their end products needed to have near zero tolerance for error. This is called quality at the source. Motorola came up with a target metric of Six Sigma to make improvements in manufacturing. So Six Sigma is aiming at a very tiny defect rate of 3.4 defects in a million. In other words, it's a defect-free rate of 99.9997%. We're only allowing 0.0003% of defects. So this is the target defect rate, defect-free rate. So to achieve this target defect-free rate, the variation across products should be small enough so that 6 standard deviations can be squeezed within the range of acceptable quality. So variance reduction is required. So I want to illustrate this with using an example. So let's say you are producing 14-inch laptops. So these are the products you produce. The first unit that's produced is 14.05 inches. The second one is 13.98 inches, and so on. So not all the laptops are exactly 14 inches. They are close to 14 inches, but not exactly 14 inches. You'll see some variations across different units. So the question is, how large variation can we allow? First, we have something called the range of acceptable quality. We're going to do a survey, and we find out that our customers are okay with our products as long as the size is between, say, 13.9 to 14.1. So they will tolerate some deviation from the target value. So this is the range of acceptable quality. And let's see how our products are distributed. So let's take this data set and let's draw the histogram of this data set. So in the histogram of this data set, on the x-axis, we have the range of all possible values for the size of our laptops. And the y-axis is the percent frequency. It tells us what percentage of data points fall within its range. So, and here is the mean, which is 14 inches. And here we have the range of acceptable quality, which is 13.9 to 14.1. Now, let's say this histogram is bell-shaped. Our data set has a bell-shaped distribution. Now, according to the empirical rule, 99.9997% of the data points are within 6 standard deviations from the mean. So remember, this is our target defect-free rate. And we want to make sure that this percentage fall within the range of acceptable quality. In other words, these data points, 6 sigma values, the values that are within 6 standard deviations from the mean should fall within the range of acceptable quality. So these are the 6 sigma values. So this is the value that's above more than 6 sigma from the target value. And this is the value that are below 6 sigma from the target value. And the values between these two should fall, because these are 99.9997%. We want to make sure that they fall within the range of acceptable quality. So to make this possible, 6 sigma, what's 6 sigma? The length of 6 sigma is this, 6 sigma, and this should be small enough so that this is less than the range of acceptable quality. In this case, it was 0.1 inch. So the standard deviation, sigma, should be small enough so that 6 sigma can be squeezed into the range of acceptable quality. And what was sigma? Sigma was the standard deviation of all the products produced. Sigma is the standard deviation of all these numbers in our data set. So in other words, the variation of our products should be small enough so that 6 times sigma is less than the width, the half width of the range of acceptable quality. So that's the idea of Six Sigma. The variance of the products should be small enough. The variance reduction is important. To summarize, we talked about the 4 dimensions of operational performance. We also talked about how a company achieves competitive advantages through cost leadership and differentiation. We learned how to measure the productivity of a process, and we talked about what reduces productivity, waste, and inefficiencies. And finally, we discussed how lean systems reduced waste through the PDCA cycle and the idea of Six Sigma.